My name is Saul and I'm going to be talking about lightnings. First, I want to give a general idea of what happens when this phenomenon occurs, and then we're going to go deeper into some details, okay? In order to understand this phenomena, we have to understand the weather situation that is necessary for this to occur, okay? So we're going to draw some cloud here. Because in order for lightnings to occur, there must be some storm or accumulation of clouds in the sky, okay? So what is going to happen in the cloud is that the heavier particles, that are the solid particles, water, are going to go downwards the cloud to the bottom of the cloud, okay? And we have the steam molecules that are going to go upwards, okay? And the steam molecules, I'm going to draw something like this. This is an oxygen and two hydrogens. This is a water molecule. It has some electrons around here, okay? It has some electrons. And the heavier particles that are the solid particles, they are heavier because they are together. They are going to attract these electrons, so they are going to steal it from these molecules. The electron is going to jump here, and it's going to go downwards, okay? And this is going to go upwards. What this is going to make is that we are going to have some charge density into the cloud. The negative charges are going to be on the bottom of the cloud, over here, because of the electrons going downwards. And on the top of the cloud, we're going to have some positive charges. Due to the protons of these molecules without the electrons, okay? So we have this charge density on the cloud, and now I am going to draw the soil, the ground, because it's the other part of this phenomenon, okay? Here's the ground, and as we know, different charges attract and similar charges repel. So we have this negative charge. What this is going to make is that the positive charges on the soil are going to go upwards and reject the negative charges, okay? So here's going to be a charge density 2, okay? Here are the positive charges. And the negative charges go deeper into the ground, okay? The same thing occurs to anything on the top of the ground. We have, for example, one house here. I'm going to draw it. And this is also going to be positively charged. Anything. It could be a human, it could be whatever, a dog, I don't know, whatever is in the ground, it's going to be positively charged. When we have already this configuration, it is obviously not in equilibrium. We have some potential difference between the cloud and the ground. Therefore, we have some electric field. I'm going to draw it just for illustrative purposes, but here we have the electric field all the way here. Because we have a potential difference between the cloud and the ground. And it's also important to say that it's not always just between the cloud and the ground. There are different kinds of lightnings. For example, this is a cloud-ground lightning. We could also have some different kind of lightnings between, for example, two different clouds. We have one cloud here and we could have another one here. Also, with a density charge density, I'm sorry, and here. So maybe the potential difference between these two clouds is bigger than this potential difference, and the jump of the electric charges are going to be between two different clouds. It could be here or here, I don't know. It is also possible that the jump of the electric charges is beneath the cloud itself. We could have some lightnings in here, and this is a cloud in the same cloud, lightning, and the lightning between clouds, and the lightning between ground and cloud. Okay? So now we have defined these things. I want to mention some important fact. When we have a conductor and it has some irregular shape, for example this, the charges tend to accumulate on the pointy ends of the conductor. So we would have, for example, a positive charge with a positively charged conductor. The majority of the charges would be accumulated on this end. Okay? It is important in order to determine where the lightning might stroke. Okay? I'm going to raise this. For example, if we have one house and like a tower made of steel, like this, that is also positively charged, and it has a pointy end, it is more probable that the lightning strokes in here because of the higher density, charge density in this end. Okay? This is because the air is not a very good conductor, so the electric charges are trying to go the easiest and the fastest to the ground. Okay, so the easiest and the fastest way to go from here to here is taking this path. The conductor, the best conductor closest to the cloud. Okay, so the lightning might go over here. Okay. Okay, now that we have defined these things, I want to say that it's not very easy to calculate the exact magnitude of the potential difference because we cannot really determine this charge over here or the charge in here. Okay, so it's very difficult to measure the potential difference and the electric field, but some scientists have found a way in order to determine those magnitudes. For example, one experiment is that you may launch a rocket from the ground to the cloud with a wire attached to the ground. So when the rocket hits the cloud, the electric charge are going to flow over this uniform wire. So it's easier to measure the voltage and the electric charges in here. Okay, but it's not very easy to do so. Okay. So what we're going to talk about next is not about calculations. So I'm going to say some facts about what makes a lightning. For example, it's thunder, what you can see and what you can hear. Okay. Now I'm going to say the difference between lightning and thunder, because sometimes people do not know this difference. Okay. And it's pretty important to know. Okay, so I'm going to draw a lightning. Like this. and this comes from a cloud to the ground, okay? So this is what you can see, and this is called a lightning. But there is also the part that you can hear, and it's called a thunder. We can understand why we can see this, because of the electrons flowing between the air, and it creates some state of matter called plasma that emits very strong, very high amounts of light, okay? So that's why you can see it. It's pretty easy to understand. But the reason that you can hear it, it's actually more abstract, okay? I'm going to draw some air particles over here. Let's suppose those are air particles, and when the lightning comes this way, it carries a very high amount of energy. So the closest particles to the lightning are going to be excited. They are going to absorb that energy, and they are going to start vibrating and heating, because heat is just the amount of vibrations in the particles, okay? So they are going to heat a lot, and I mean like really, they are going to get really hot, okay? So as they are moving really fast, they are vibrating really fast, they are going to make these colder particles to go away. So the heat particles, the warm particles, are going to move that fast that the colder ones are going to move away from it. And that movement is what you can hear, okay? This is going to produce some waves, some mechanical waves that are going to travel into the air to your ears, and that's what you can hear. Also, there is a very interesting fact about this, that usually you see the lightning first and then you hear the thunder like some seconds after, okay? This is because obviously light travels a lot faster than the sound in the air, and the light reaches to your eyes a lot faster than the sound to your ears. So now, in order to conclude, I want to talk about maths, not really physics. I want to talk about a mathematical entity called a fractal, okay? So I'm going to erase this. Now I'm going to explain you what a fractal is. A fractal is a mathematical entity that self-replicates itself. What this means is that it looks in a similar way when you look at a scale, and when you get closer or a different scale, it might look similar. A very famous mathematical fractal is the Sierpinski triangle. Okay, so we would define this in this way. It is a triangle. I'm going to use it. It's a triangle. And now I'm going to divide this triangle into 4 triangles. How am I going to do this? I'm going to take the half of this line, and I'm going to join these points. And now I have 4 triangles, 4 different triangles. And I'm going to take this out. This is going to be a hollow, okay? And I'm going to continue doing this in this triangle, and this triangle. Ideally, this would go forever. With this, and it would continue like forever. So if you look at this scale, it looks this way. But if you isolate this triangle, it will look similar to the complete fractal. The same way, if you isolate, for example, I'm just going to draw this part a very small triangle, if you isolate this triangle here, it will look similar to the complete fractal. Fractals look very perfectly defined in the mathematical realm, but in the nature there also occur some fractals. One example of this is the lightning. When you have the lightning structure, something like this, and it has some branches, you can see that this is also a natural fractal, because if we take this complete image and we, for example, isolate this branch, we see that it has similar behavior to the complete lightning. It has a starting point and then it shifts directions in a very unpredictable way, actually. And if we isolate this, we might see that here you have smaller branches coming out of this part. So a lightning, it's a very interesting way to look at fractals in the nature. Okay, and with this I want to conclude. I will also leave a link into the description of this video to a computer science project that I made on fractals, so you may want to check it out. It's very interesting and it might let you understand this better. Thank you.